Today we're going to begin our discussion of solutions, and we're going to begin that discussion by talking about water for a little bit. Water is called the universal solvent. Water is essential for maintaining human life because a lot of the reactions that happen inside of our body, and also just one of those solvents that we need to survive. That's what keeps us alive. So another way, like outside of our body, the water can affect human life is to help moderate the Earth's temperature because water vapor is actually a greenhouse gas. Water is also used to cool engines, the nuclear power plants, so there's no explosions there, and water is used in lots and lots and lots of industrial processes. Water, it used to be more significant, but it's still significant in terms of a means of transportation on the Earth's surface. Water it's a polar solvent, so it does possess the ability to dissolve many substances. Liquid water is H2O. Actually, solid water and gaseous water are also H2O. But the structure of a H2O molecule, when you're looking at Vesper theory, which we'll get to later on in this course, is bent. The angle that it maintains is about 104.5 or approximately 105 degrees. And the reason it is bent that way and not just basically 90 degrees or not straight at 180 degrees is because the oxygen atom has unpaired electrons that occupy more space than the bonded electrons to the hydrogens. Because water orients itself this way, it's considered polar, so it has an unequal distribution of charge. So partly it's a polar molecule because it's oriented that way. Partly it's a polar molecule because oxygen is more electronegative than hydrogen. And so oxygen, because it has 8 protons in its nucleus, will pull the electrons closer to it than closer to the hydrogen that only has 1 proton in its nucleus. So water can hydrate other molecules because what it does is if the particular anion or particular molecule has a negative end, the positive end of the water molecule is attracted to that, and then if what you're trying to dissolve has a positive end, then the negative oxygen end is attracted. And with salts, and generally speaking, a salt, according to most consumers, is sodium chloride, but there are a lot of salts in chemistry because an ionic compound is simply considered a salt. And when you put a salt into water, it will break into its positive and negative ions, and then those water molecules will be attracted to those positive negative ions and orient themselves according to the positive and negative portions of that polar water molecule. This is an animation of how that happens. So here we have a salt, a big chunk of salt, and that salt has positive ions, the sodium ions, and it has negative ions, which are the chloride ions. And notice the chloride ions are much larger because they do have more protons, and they do have a larger radius because they have more electrons as well. So notice how the water molecules are oriented themselves. So here's a negative chlorine, and the positive end of the water molecules are orienting there. Here's a positive sodium, and the negative end the water molecules are orienting there. And as that continues, as that salt continues to be placed in the water, then you have these little pieces that come off, and they are thoroughly dissolved in the water. So when ionic salts dissolve in water, they completely break into their individual cations and anions. So in this example, we have ammonium nitrate, and it's a solid. When I put it in water, so notice on top of the reaction arrow, there is liquid water. We do form ammonium ions, aqueous ammonium ions, and aqueous nitrate ions, because those ions don't just exist floating out there all by themselves. They're not stable that way, but they are stable being dissolved in water. So solubility of ionic compounds. So not every ionic compound falls completely apart like that. Some have a higher attraction to the ions inside of themselves than to the water that's surrounding them. And so the solubility is not the same in every ionic compound, but generally speaking, ionic compounds are soluble. We'll talk later in this chapter about solubility rules. Notice the example at the bottom of this slide says sodium chloride is quite soluble in water, so that means you can put it in water, it will completely break down, whereas silver chloride is only slightly soluble. Silver chloride in water exists as silver chloride salt. It does not break down into silver ions and chloride ions. Water can also dissolve many non-ionic substances. Like, for example, ethanol. Most alcoholic beverages contain ethanol that is not pure because it's an aqueous solution. And that ethanol also has a polarity to it, which makes it soluble in water. So generally speaking, we use the like dissolves like as a useful rule for predicting solubility. There will be some exceptions. For example, you just saw one in that silver chloride. Like dissolving like is also very beneficial in your home. If you have a stain in something, it's useful to determine what that stain is in order to be able to predict a solvent to get it out. So here's that structure of ethanol. Notice here's a polar bond. It's an oxygen-hydrogen, just like in the water. That oxygen-hydrogen polarity is going to be what attracts that water molecule, and that's what helps it to dissolve in water. What if no ionic solids were soluble in water? How would this affect the way reactions occur in aqueous solution? Again, that's just kind of a thinking question, but there are a lot of things, especially in our bodies. We have to have ions in our bodies for reactions to happen, and your nervous system to work correctly, as well as other systems. And so the only way to get those reactions to occur would be to supply a whole lot of energy if they weren't already soluble in water. So water, we've already mentioned, is the universal solvent. We're going to start talking about solutions now, because this chapter is based a lot on solution chemistry. A solution, another name for a solution, is a homogeneous mixture. A homogeneous mixture means it's the same throughout. Now, it is the same throughout. However, the way that it differs from a chemical compound is it can have a differing concentration. So, for example, if the dentist says to me, go home and gargle with some salt water, chances are, if they tell you the same thing, you're not going to be gargling with the same amount of solute dissolved in the solvent as I am. By chance, it might happen, but homogeneous mixtures are simply solutions, but they can have a varying composition. So by definition, the substance being dissolved is the solute. The dissolving medium is the solvent. So in most cases, what we're going to talk about, the solvent is water. And the solute-solvent combination makes a solution. Solutions can have the ability to conduct electricity. And you've probably seen this before if you've ever seen like the lemon experiment, where you put 2 electrodes in a lemon and it lights the light bulb up. That just means that it can conduct an electrical current. Pure water is not an electrical conductor. It has to have things dissolved in it. You'll see, people will argue that, oh, water can't carry, like, for example, your tap water can't carry an electric current, so you can't get shocked in the shower. However, the water coming into your shower is not pure water. It's not pure H2O. It has different things dissolved in it to make it safe for you to use. If a substance in a solution is able to conduct electricity, it is considered an electrolyte. And there are strong electrolytes and there are weak electrolytes. So if you look at this particular example, notice that A has many ions, and so the light bulb burns very brightly. B has very few ions in it, and so the light bulb glows very dimly. And then C has no ions, and so the bulb does not glow at all. And so if you look at it, you'll notice here in A, there's several ions there. In this particular example, only a little bit of it dissolved, and so you only ended up with 2 ions, where on A, every one of these is an ion. In this, notice that none of these have any charges on them, so therefore it is not an ion at all. If something is it conducts current very well, like in example A, that's considered a strong electrolyte. If it conducts a small current in aqueous solutions, so for example, acetic acid, the basis of vinegar, will conduct a small current because it breaks apart a little bit, but not every single molecule of acetic acid breaks apart. Considered a weak acid as well as a weak electrolyte. And then a non-electrolyte would be sugar, because sugar does not break into ions at all. And so if it's put into pure water, it doesn't change how the current flows. So when talking about strong and weak electrolytes, a man named Arrhenius, he was looking at these conductivities, and actually Arrhenius gets lent to the namings of particular acids, and so things can be Arrhenius acids or Arrhenius bases based on their ability to exchange electrons or protons. But his first research, according to this, was he postulated that to the extent to which a solution conducts an electric current directly depends on the number of ions present. So a strong electrolyte is completely ionized. That means every single particle or every single formula unit will actually be dissolved in water. There are soluble salts, there are strong acids, and there are strong bases. Soluble salts, most often chemistry text will use sodium chloride as your example of a soluble salt. Some different strong acids, and please note that a strong acid doesn't mean it's more harmful to you. It simply means, by definition, a strong acid is one that completely breaks apart in water. So if I put hydrogen chloride in water, then I won't have hydrogen chloride. I will only have protons, which are H pluses, and chloride ions. If I put nitric acid in water, I won't have HNO3. I will only have H plus and NO3 minus. And sulfuric acid, at least that first proton, the same as well. I will only have H plus and HSO4 minus. And notice all of these produce hydrogen ions when they're dissolved in water, and so they are considered acids. Acids will dissolve in water simply because they are polar as well. And so that's why here's a generic statement as to what happens with a strong acid. And as we mentioned before, those are examples of 3 strong acids. Strong bases, most strong bases contain the hydroxide ion. And so again, same kind of thing, only this time we have a solid potassium hydroxide. We put it in water. We only have potassium ions, and we only have hydroxide ions. Now, not all hydroxides are soluble, but there are a few strong bases that are soluble in water, and they're considered strong. They are considered strong electrolytes. Weak electrolytes, you'll get a small amount of ionization. Weak acids and weak bases fit into this category. And just kind of thrown in here, writing formulas for acids. Any atom that produces hydrogen ions in solution is listed first. So that would be most of the time, that would obviously be your H. So that's why it's HCl, and that's why it's HNO3 instead of the other way around. Non-acidic hydrogen ions are written later, and basically that means we could have something like sodium hydride. This is not an acidic hydrogen because it is listed second and not first. Here's an example of what a reaction looks like when you put a weak electrolyte in water, and this is acetic acid. So acetic acid added to water. Notice the arrow. The arrow means there's an equilibrium that will exist. So this will dissolve to a certain extent and make hydronium ions, which is just an H plus combined with a water, and acetate ions. But it is an equilibrium situation. So anytime you see this, that should automatically signal to you that that's a weak acid or a weak electrolyte. And we can push this reaction back and forth because of that double arrow. And a weak base, ammonia is a weak base. It's basic because it produces hydroxide ions. Again, we have a double arrow, which means the reaction can go both directions. So that ammonia steals a hydrogen from the water, makes ammonium ion, and then that leaves hydroxide left over. Non-electrolytes do not produce any ions, and so ethanol, even though it's soluble in water, it didn't produce any ions. It just had a polarity to it. Table sugar, soluble in water, not a whole lot of polarity to that. So just a few quick questions. Which of the following solutions contains the greatest total ion concentration? 1 mole of potassium chloride dissolved in 1 liter of solution. So notice all of these are 1 mole dissolved in 1 liter of solution. So if we write the formula, potassium chloride is just simply KCl because potassium is a +1, chloride's a -1, so that's the formula for potassium chloride. Iron 2 nitrate, the 2 tells me that the iron is a +2. Nitrate, we should know by now, is a -1, and so when I move these around, when I crisscross, then I end up with iron 2 nitrate written like that. Potassium hydroxide, potassium's a +1, hydroxide is a -1. That's the formula for potassium hydroxide. And then sodium phosphate, sodium's a +1, phosphate is a -3, and so if I cross those, I end up with Na3PO4. Now the question is, which of the following solutions contains the greatest total ion concentration? And so we're dissolving the same amount, or same moles of each in 1 liter in the same amount of solution. So when this breaks apart, it's going to become K plus and Cl minus. When this one breaks apart, it's going to become Fe2 plus 2 nitrates. So this one will become K plus OH. Now remember, those polyatomics need to stay together. And then when this one breaks apart, it's going to become 3 sodiums plus a phosphate. So the answer to this question is D, because when we break this apart, we get a total of 4 ions on the right-hand side. This one we get 2. This one we get 3, and then this one we also get 2. So the correct choice on this one is answer choice D. Which of the following statements is true? If a substance is soluble, it must be an electrolyte. That is not true, because remember, ethanol is a non-electrolyte. If a substance is an electrolyte, it must be soluble. I would venture to say that is true, but let's look at the other ones. Weak electrolytes must be less soluble than strong electrolytes. That's not necessarily true, because it may be more soluble, but it just doesn't have as many ions, and the same kind of thing as on the last one. Non-electrolytes are non-soluble, and so the correct choice on that one is B. Well, that concludes lesson 4-1-2, which begins our discussion about water and solutions. In the next lesson, we will talk about how to determine the composition of solutions and how to indicate that.